Okay, folks, continuing right along, we're going to get into another one of our famous E words, enthalpy. So hopefully you remember that from your previous classes. So we're going to go through the thermodynamic definitions and some equations describing enthalpy. And I do want you to know those equations. So there's a nice little statement here that I grabbed from Atkins that I think kind of sets up our equation nicely. Delta U is not equal to the energy transferred as heat when the system is free to change its volume. So if you recall, when we looked at U, changes in U, when we imposed constant volume, it's only equal to the heat delivered. So when there's constant volume, there is no work done. We're going to flip the script now, and we're going to impose constant pressure, but allow the, oops, I wrote V. We're going to impose constant pressure, but we're going to allow the volume to change. And if we imagine this situation here where we're heating up some material, right? We're pumping energy into it. Most materials will expand when they are heated. And thus, as they are expanding, they're doing work against the surroundings. So that means now when we've allowed that volume to change, delta U is not equal to that energy transfer. It's actually what we refer to as the enthalpy. So here we have the hard definition of enthalpy. H is U plus PV. And we're going to play this game with calculus. We're going to allow H to tend from H to DH. We're going to allow U to tend from U to DU. Of course, we're going to allow P to tend from P to DP, and we're going to allow V to tend from V to DP, V to DV, excuse me. So we're going to put all of these relationships in here and see if we can't work out something a little bit more fundamental. So I'm going to say H plus DH equals U plus DU plus, now we have the quantity P plus DP times V plus DV, okay? And we're going to separate those out through the process of FOIL. So let's keep going with that. We've got, and I'm going to actually start that on the next line. So I've got room. So we have H plus DH equals U plus DU. And now I'm going to FOIL the sucker. So first is going to be PV outside. So that's going to be plus P dV. Inside, that's going to be V dP, and last, that's going to be dP dV. So now we want to inspect this for any kind of simplifications that we can make. And hopefully what we can see right away, we've got a U plus PV right here, U plus PV, and we've got an H. So by our original definition, U plus PV just equals the enthalpy. So we can see now that H and H will cancel, so we're all good there. We've imposed that pressure must be constant. So because pressure is constant, that means dP is equal to 0. So we know that this term will drop out. And then finally, when we have dP times dV, those are two infinitesimally small changes being multiplied by each other. So we will approximate that those are 0, right? Two very, very small things being multiplied by each other will give us, an even smaller thing. So what we are left with is the following. dH equal, said dH and I wrote du. Let's try that again. Okay, so what we have now is dH equals U plus PdV, okay? So we can't for, oops, and I wrote U, but remember U plus PV was canceled out, so that's du. Apologies. I'm not going to re-record, I'm just going to keep going with it. So dH, du, and PdV, that's everything that we had left. Okay, goodness. So we've got to remember the first law. So always, when in doubt, remember the first law that says du equals dq plus dw. So let's replace du with the first law. So we've got dh equals dq plus dw plus pdv. Well, we remember that dw is equal to negative p dv, and we're allowed to make that substitution because our volume is free to change. So substituting that in, we've got dh equals dq minus pdv plus pdv. So you can see those are canceled, and the only thing we're left with is dh equals dq, and I'm going to put a little p right there to note that we have constant pressure. Okay. And this is where I like to point out now that we've got what I like to call the twins. So we've got dH equals dQ plus dP. I'm going to write twins here in red. And then I'll also just remind you, right, that we know that du was equal to dQ at constant volume. So these are what I will refer to as our twins. Enthalpy is heat delivered at constant pressure. Internal energy is heat delivered at constant volume. And we will see a number of equations in the coming sections to calculate the change in enthalpy. So let's talk about condensed phases versus gas phase for enthalpy changes. And so remember, we set up this scenario with the idea that we're heating some liquid or perhaps some solid, and most of those materials will expand when they're heated. So if we draw a little picture of a beaker of some liquid, let's say, okay, and we add heat, so that sometimes that delta sign is used to say heat. So our liquid is going to expand, but it is going to be barely discernible. Only expands slightly. Okay? So what that means for condensed phases, this quantity PV, and notice that I've now just indicated it with respect to the per mole unit, so that's what the M is for. This quantity PV will basically drop out to 0 because we expect our solids and liquids only expand ever so slightly. So what that means for condensed phases is the enthalpy is very closely related to the internal energy. They're almost identical. So that's condensed phase, so solids or liquids, okay, liquid or solid. For the gas phase, however, when we heat up a gas related to our gas laws, it's going to change volume enormously. So we can't ignore that PV term. So, and if we think of this in terms of an ideal gas, right, we can replace PV with nRT, right? PV equals nRT. And we can see that the enthalpy and the internal energy for a gas will be very different. And if we apply this change, if we say for measurable changes, delta H is going to be equal to delta U. R and T are constants here. So in terms of a chemical reaction, that will really be manifested in delta N RT, okay? So that's for chemistry, right? Some chemical change. Or if we can imagine a physical change, I can't talk and write my letters at the same time. So for a physical change, perhaps where there is no change in number of moles, right? That's going to go in our delta T. So that would be a physical change, right? Like heating something up into a new phase or something like that, okay? So these will be very different for gases. Whereas for a liquid and a solid, the enthalpy and the internal energy are very closely related. Okay, we're going to keep going down the rabbit hole with enthalpy in the coming videos.